Welcome to the Crazy Hat Chemist. Here we go. Today is the fourth video in a series of 5 on chemical reactions. And today we're going to specifically talk about balancing equations using fractions. Okay, so here we go. Bam! Okay, fractional balancing really applies when we have diatomics. Now it can apply with other things as well, but it really works very nicely with diatomics. And we're going to be multiplying by a fractional coefficient. That's our multiplying factor. Okay, I'm hoping that you remember your diatomics. Okay, remember there's an L on your forehead. You're going to flip that L down and you get the number of 7. That number 7 tells you how many diatomics there are. Okay, and these are the diatomics. I've highlighted those for you there. So these are the diatomics. You're going to flip this down, you got a number 7. Okay, there we go. There's our diatomics. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. Okay, so here we go. If you're going to subtract 1 in front of the diatomic, you're going to multiply by half. If you're going to add 1, you're going to multiply by 3/2 stoichiometric coefficient. If you're going to add a certain number, that's z, which is going to be an odd number, it won't be an even number, then you're going to multiply by z over 2. Now, it could be an even number if there's an oxygen in another compound, so those are special cases, though. All right, so here we go. Number 6. Write a balanced equation when plumbic oxide is heated in the absence of air. Again, we're going to go back to our chemical reactions and types and figure out what type of reaction this is. We're going to figure out what plumbic is. Plumbic is a 4+ charge. Oxide is a 2- charge. I'm going to take the 4 and the 2. I'm going to take the absolute value of the 4 and the 2. I'm going to take the bull by the horn, flip, bring it down, and I get the following. Then I'm going to reduce this. There's a common factor of a 2. I'm going to reduce that. Okay, it says in the absence of air, so there's no oxygen, there's no other reactant. And so here is what I have. It is a decomposition type of reaction here. So that's plumbic oxide, that's a solid, okay, it's heated in the absence of air. Now I need to figure out, since it's a decomposition reaction, I need to get a gas and either a California or an element. I'm not going to get a... I am going to get a gas, and the gas that I'm going to get is oxygen gas. What's the formula for oxygen gas? That's that L on your forehead, flip down, and I got oxygen gas, so that's an O2. Now the other product, because lead has 2 different charges, then the other charge on lead is a 2+. So I'm going to take the 2+, the 2- for the oxygen, take the absolute value of those 2 numbers right there, flip, bring it down, and then I'm going to reduce it to PbO. And now here is my products. Okay, so hopefully that's okay for you. So now what I'm going to do is I'm going to take a look at how many I have on both sides to do the balancing. How many leads do I have on the reactant side? 1 lead. How many leads on the product side? 1 lead on the product side. How many oxygens on the reactant side? 2. How many oxygens on the product side? There's 1 oxygen in plumbous oxide, and then there are 2 oxygens in molecular oxygen. So that's a total of 1 + 2, that's 3. So I have 3 oxygens on the product side where the diatomic is, and I have 2 on the reactant side. So I need to decrease the number of oxygens on the product side by 1. So I'm going to put a stoichiometric coefficient in front of the molecular oxygen so that I get rid of 1 of the oxygens that is there. So when I put that stoichiometric coefficient of a 1/2 in front of the molecular oxygen, 1/2 times the 2 in O2 gives me 1 oxygen, and now this equation is actually balanced. So you're going to have to ask your instructor if this is okay to leave fractional coefficients. I'm going to say no, so just in case. So we're going to get rid of that fractional coefficient. So we're going to multiply by the denominator of that fractional coefficient. The denominator of that fractional coefficient is a 2. So I'm going to multiply the entire equation by a 2. That's what this is right here. So now I'm going to distribute that 2 over all the terms, and then I get the final balanced equation. And again, you should check to make sure that everything is balanced here, but it is in this case. All right, fantastic. That's balancing equation number 6. We got 2 more balancing here with fractional coefficients to do. Here's number 7. We're going to write a balanced equation when lithium aluminum hydride is heated in a vacuum. This is lithium aluminum hydride. I don't expect you to know this formula. That's kind of beyond the scope of this here. And then I'm not expecting you either to get the products. But this is a decomposition reaction because there is no other reactant. These are the products. But I am using this just so that you can use fractional coefficients for balancing. So first I'm going to do is I'm going to check the lithiums on the reactant side. There's 1 lithium on the reactant side. How many lithiums on the product side? 1. How many aluminums on the reactant side? 1. How many aluminums on the product side? 1. How many hydrogens on the reactant side? 4. How many hydrogens on the product side? Sorry, how many hydrogens on the product side? 1 in lithium hydride and 2 in molecular hydrogen. So that's a total of 3 hydrogens on the product side and 4 on the reactant side. So I actually need 1 more hydrogen where the diatomic is. So I need 1 more. So I'm going to add 1. So I'm going to multiply by a 3/2 in front of the hydrogen. So 3/2 times 2, that's because of the H2. 3/2 times 2 is 3. So 3 plus the 1 in lithium hydride is 4. So this equation right now is actually balanced. But just like on the previous one, I do not want to leave fractional coefficients. So I'm going to multiply the entire equation by the denominator of the fraction in which I used. And that is a 2. So I'm going to multiply the entire equation by a 2. Once I multiply the entire equation by a 2, this is what I get right here. And now that is balanced. All right. You guys are moving really well. So let's keep on going. We got 1 more to do in this here lecture. Bam. Here's number 8. Write a balanced equation when liquid octane burns. So first of all, burns, and we're going to figure out what type of reaction it is. It's a C and an H, and it's any number of C and an H, and it burns. So that burns tells you it's a combustion reaction. That burns tells you that the other reactant is going to be molecular oxygen, and that's O2. So here are my 2 reactants. I got the liquid octane, and I've got molecular oxygen. There's the delta for any combustion reaction. What are the products for every kind of combustion reaction that we're going to be dealing with here? That's right, that's carbon dioxide and water. Okay, so it's a combustion reaction, and it is carbon dioxide and water. Okay, now I did tell you at the very beginning of this unit that you need to balance combustion reactions in a particular order. That particular order is first, carbons, second, hydrogens, third is oxygens, and the diatomic, specifically molecular oxygen at the end. So that's the order that we're going to follow. So how many carbons do I have on the reactant side? 8. That's why I'm going to put an 8 stoichiometric coefficient in front of the carbon dioxide. Okay, how many hydrogens do I have on the reactant side? 18. How many hydrogens do I have on the product side? 2. So it's 2 times what number gives me 18? That's a 9. Okay, so now what I'm going to do is I'm going to check and see how many oxygens I have on the product side. So how many oxygens do I have right here? So that's an 8 times a 2, and that gives me 16. How many oxygens do I have right here? That's 9 times a 1, that's 9. Now I'm going to sum up the 16 and the 9, and I'm going to get 25. Okay, so let's just pretend for a moment. Let's say this 25 was not a 25. Let's say it was a 24. If that number was a 24, then what would be the stoichiometric coefficient in front of the molecular oxygen? Just give you a moment. That should be a 12. Okay, so anytime you have an even number, it's really easy. But unfortunately, this is an odd number. So when it's an odd number, you're going to take that odd number, whatever that odd number is, in this case it's 25, and we're going to say 25 over what number? So we're using fractional coefficients, so it's 25 over 2. So now I'm going to put that 25 over 2 in front of the molecular oxygen. This equation right here on line number 5 here is actually correctly balanced right now. But in order to get rid of that 2 in the denominator, I'm going to multiply everything by that 2 in the denominator. And now this is what I get for my balancing of this equation. Okay? Everybody okay with that? Okay, you should check to make sure you have the same number of carbons on the reactant and product side, the same number of hydrogens on the reactant and product side, and the same number of oxygens on the reactant and product side. But I guarantee you it is balanced. Okay? And I'm the king here today, and so that was the fourth video in a series of 5. I can't wait for the net ionic equations. That's going to be the next one, and then we're going to be done with this unit on chemical reactions. I hope you have a fantastic day. I'll see you later. Bye now.